next problem is to solve using power series the ordinary differential equation y second derivative plus k squared times y equals 0. We know first that the general solution of that is a times cosine kx plus b sine kx and a and b are any constant numbers, but I will solve it using the method of series. So for that method we suppose that my solution is written in the form of a power series, so it's written like that. Then I take the first derivative, and the first derivative is the same sum of n c n x to the n minus 1 power. It's easy to find that if you take the derivative of that expression, it is this. Then we differentiate two times and we find the second derivative. Second derivative is it starts from 1 here. Yeah, that's very important, because if we take 0 we will have a negative exponent, and we must not have a negative exponent here. Also here we start from 2, and this is n minus 1 cn 2x n minus 2 power. Then I have my function, I have the first derivative, I have the second derivative, so I have to substitute them into the differential equation, and after substitution I have sum from 2 to infinity of n minus 1 cn x to the n minus 2 plus k squared sum from 0 to infinity of cn x to the n power. All this is 0. Now you see that I have a little problem here, because this sum starts from 2 and this sum starts from 0, so I have to normalize them, and I want to make this sum every one of the sums starting from 0, so I want this sum start from 0 too. For this I take n equals 0 to infinity of n plus 2 n plus 1 cn plus 2 x to the nth power. Also I create the same power, that's x to the n, x to the nth, and the other one is k squared sum from 0 to infinity of cn x to the nth power. Now what happened here is that since this index starts from 2 and I want these to start from 0, I lower the index 2 units and I increase n by 2 units. So in the place of n I have n plus 2, in the place of n plus 1 minus 1 I have n plus 1, in the place of n I have n plus 2, and now I can collect all the expressions into one. So I have here n plus 2 n plus 1 cn plus 2 plus k squared cn x to the nth power equals to 0. Now since all this expression is 0 and this power series is 0, this expression must be 0, and from here we get cn plus 2 equals to, again, we will write it again, so we have cn plus 2 equals minus k squared n plus 2 n plus 1 times cn for each n that's greater or equal than 0. Now we have to see what happens here for some successive values of n. So I substitute n equals 0 and I have c2 equals to minus k squared over 2 times 1 c0, and that's minus k squared over 2 factorial c0. I'm doing the same with n equals 1 and I'm getting c3 equals minus k squared over 3 times 2 c1, and that's minus k squared over 3 factorial c1. Then I have for n equals 2, C4 equals minus k squared 4 times 3 C2, that's minus 1 squared. I substitute C2 here, that expression, and I have k squared over 4 times 3 times 2 times 1 C0, and this is minus 1 squared k squared over 4 factorial C0. In the same way, we find for n equals 3 that C5 equals minus 1 k squared 5 factorials times C1. So you see a different behavior of the coefficients related to what the index is. If the index is positive, if it's even or odd. So let's have two cases. Suppose n is of the form 2m minus 2, then we find C2m equals to minus 1 to the m power k squared 2m times 2m minus 1 up to 1 times C0, and this is minus 1 to the m power k to the power 2m over 2m factorial C0. Again, in the same way, if we substitute n by 2r minus 1, we get C2r plus 1 equals to minus 1 to the r power k squared 2r plus 1 to r to 1 times C1. That's minus 1 to the r power k to 2r power 2r plus 1 factorial C1. It's valid for m greater than 1, it's valid for r greater than 1. Now, my general form of y of x is C0 plus C2x squared plus C4x to the 4th power plus C2m x to the 2mth power. And so I separate actually the odd terms, and I separate the even terms, and I separate the odd terms here, and this is C2r plus 1 x up to infinity. And now when I substitute my coefficients as I found them before in this expression, I have 1 minus k squared over 2 factorial x squared plus k to the 4th power over 4 factorial x to the 4th power plus minus 1 to the m power k to the 2m power over 2m factorial x to the 2m power. And here for the second part I have c1 over k times kx minus k cubed over 3 factorial times x cubed. The same for the fifth power and the general expression here. This is 2r plus 1. So what we see here, if we remember the Taylor expansion, this Taylor expansion actually is cosine of kx, and that Taylor expansion here is sine of kx. So this is the general form of the solution that coincides with the form we take when we use the normal theory of the differential equations with constant coefficients.